everyone. Welcome to the Center for International Security and Cooperation at Stanford University. Thank you for joining our weekly research seminar. It's a great pleasure to introduce our speakers today. I'm Harold Shinkunas, I'm Deputy Director at CSAC, and let me go on to introduce the speakers. Dr. Silgi Park is CSAC Nuclear Security Fellow. She has a PhD in geological sciences from Stanford University. She is focused on understanding the front end of the uranium pathway in North Korea, and she'll be speaking to us today about some of her research. She is joined by Alison Puccione, who's a CSAC network affiliate. She has a long career as an imagery analyst. She's principal and founder of Armillary Services, providing insight on commercial imaging satellites and associated analytics. And she also manages a multi-sensor imagery analysis team at CSAC. So we're looking forward to hearing from both of them to discuss North Korea's nuclear fuel cycle. Before I turn over to Dr. Park to lead off the talk, there'll be an opportunity for Q&A at the conclusion of their talk after about 35 or 40 minutes. Please go ahead and enter questions in the Q&A box on Zoom at any point during the talk. After the talk concludes, I'll come back to manage the Q&A. Over to you, Dr. Park.
Harold, thank you for the introduction and thank you for everyone who's joining us today. I'm delighted to share my research with you and I look forward to hearing the feedback during the discussion section. So if you remember, the Singapore summit in June 2018 between Trump and Kim started off with an upbeat in hope that the two countries can take active steps in de-escalating nuclear tensions over the Korean Peninsula. But the follow-up Hanoi summit in 2019 ended on a sour note with no fruitful results. The year 2020 and the global pandemic saw no exception to North Korea's proliferation activities. The core nuclear facilities in North Korea remain not only operational, but active, posing a deep concern on the international security today. North Korea's intent for nuclear armament remains quite clear, and that necessitates a solid understanding on the kind of capacity that North Korea has on building its nuclear arsenals. With that, we would like to share with you part of our ongoing research in which we look at North Korea's overall nuclear fuel cycle from its capacity to produce its fissile materials to the overall activities and pathways of the main bomb production system. We use an interdisciplinary approach to address our research questions. So in answering the first question on the fissile material precursor productions, we combine historical archives with the geological toolsets. And in monitoring the ongoing activities, we utilize commercial satellite imageries, sometimes combined with computer vision algorithms. So if you do have time at the end, we can showcase an example in which we applied artificial intelligence over satellite imageries to track proliferation activities. But if we do run out of time and if the audience is interested, we can defer the part to the next week's talk. Let's begin with a short historical context that highlights some of the major events relevant to the talk today. Now, North Korea started exploring its uranium as early as 1940, so that's predating the Korean War. In 1959, it had a nuclear cooperation agreement with the Soviet Union, which accelerated its uranium exploration processes. So in 1960s, they explored deposits over Wongi, over Pyongsan, Hamhung, and Haegungang. In the 1980s, North Korea started building its nuclear reactors, including the 5 megawatts at Yongbyon. For 5 years after that, with the effort led by the United States, North Korea successfully signed the Non-Proliferation Treaty. Now, that treaty has led to IAEA inspections in 1992, during which North Korea declared 2 uranium mines and 2 uranium mills. The 2 uranium mines included the Suncheon Warbisan mine and Pyongsan uranium mine, and the 2 uranium mills included the Pakcheon pilot plant and Pyongsan uranium concentrate facility. Among these 2 mines, information on Suncheon Warbisan mines suggests depletion and possible decommission. And as with the Suncheon mine, Pakcheon pilot plant was declared decommissioned in the 1990s. So that makes Pyongsan uranium mine and milling facility as the only remaining verified source of uranium ore in North Korea today. In 2002, North Korea famously withdrew from the NPT, and ever since then, there has been periodic moments where North Korea would shut down and suspend its nuclear activities, usually following some form of agreement such as the 1994 bilateral framework. But operation always seems to resume. Now, when I say operation resumes, I mean it for all stages of North Korea's fissile materials pathway. The pathway begins with the extraction of uranium ore at the mine, which is then converted into tri-uranium octaoxide known as the yellow cake at the milling facility. Now, yellow cake can typically be converted into uranium hexafluoride, enriched to increase the content of uranium isotope 235, fabricated into uranium dioxide metal pellets to be used as a fuel in a nuclear reactor. Now, this trend might supply fuel to the light water reactor or the experimental light water reactor at Yongbyon with the stated purpose of electricity generation. But as Alison will tell you a little bit more later on, this ELWR experimental light water reactor in North Korea is not operational today, mainly due to technical difficulties rather than the diplomatic reasons. So the only active and continuously operating reactor is the 5 megawatts. And this gas-cooled graphite moderator reactor can intake unenriched uranium directly, thus simplify the fissile materials pathway a little bit. Now, operation of the nuclear reactors generates spent fuel from which fissile materials can be reprocessed in the form of plutonium, a weapons-grade material. And the other weapons-grade material, highly enriched uranium, can come from the enrichment facilities directly. As I stated earlier, mining and milling of uranium occurs over Pyongsan in North Korea, and the rest of the processes occur at Yongbyon and to a lesser extent at Gangsan, although the main purpose of Gangsan is still under debate. So we're going to walk through our analysis over each of those steps, and it's a pretty dense presentation. So to guide you along the talk, the step that we're discussing will be emphasized at the top right corner of each slide. So let's begin with the mining. Given the heavy sanctions against North Korea, mining of uranium is really the first and the most rate-limiting steps in the production of fissile materials that are required to make nuclear weapons. There's only one verified site, and much of the information on the site really depends on analysis over satellite imageries. But we still do not have a consensus on the types of uranium that's being mined, the quality of uranium, or the volume of the ore therein. So I try to answer those questions from geological perspective. And geology really plays a dominant role in at least the front end of the uranium production pathway. It tells us where and when which minerals to be explored or exploited. It governs the design of the mines or the types of mining techniques to be used. And it provides a means for commissioning, for operating, and for decommissioning the mines. So I looked at numerous geological maps of North Korea that were published by multiple institutions across the world. And so these institutions include those from Japan, from China, from Russia, from South Korea, as well as from North Korea. And for those who are unfamiliar with such maps, each of these color blocks and patterns represent a specific type of rocks, the corresponding ages in mineralogy. And it can be quite descriptive. For example, this map from the 1990s is displaying over 150 different types of rocks in Korean Peninsula. Information from the maps were then combined with the defector accounts, peer-reviewed field geology reports, as well as the first-hand collection and analysis of comparable rock samples that I collected from South Korea. Now, just to clarify, these reports include geochemical literatures published by the Russian and Chinese geologists who had the access to the country to conduct extensive geological survey. Analysis from these toolsets indicate that Pyongsan uranium mine is primarily composed of metasedimentary rocks dating back to the Mesoproterozoic eon. So that is metamorphosed sandstone or siltstone that are 480 to 1600 million years old. Field geology reports indicate that uranium in North Korea is commonly found in the form of coffeenite or uraninite in carbon shells. Geochemical literature also makes a correlation between the sulfide minerals, including pyrite, as well as trace elements including vanadium and nickel with these uranium-bearing rocks. Now, we don't have a lot of detailed sampling analysis from Pyongsan to help us identify the ore grade, but luckily, a lot can be learned from a very comparable geologic setting at the Okja Metamorphic Belt. Okja Metamorphic Belt, or the OMB, is the only major uranium reserve in South Korea. And despite the political boundary, these two sites are really geologically related. Just like the Pyongsan uranium mine, Okja Metamorphic Belt is composed primarily of metamorphosed sedimentary rocks dating back to the Precursoric eons, so it's similar types of rocks in the same age range. There, uranium is again found in the form of uraninite, as well as uranothorite that are chemically compositionally similar to coffinite. Geochemists in South Korea also makes correlation between sulfide minerals as well as trace elements with such uranium-bearing rocks, thus highlighting the geochemical resemblance of these two sites. But unlike Pyongsan mine, now we have a lot of detailed samplings from Okja Metamorphic Belt, which tells us that the grade is between 0.026 to 0.036 weight% uranium, and the deposit type at Okja Metamorphic Belt is metalliferous black shale. So these comparable geological settings, with the similar geology, similar mineralogy, petrology, and the available geochemical information suggest that Pyongsan deposit is metamorphosed organic shale similar to the black shale of the Okja Metamorphic Belt. And if so, the geological settings of such deposits at Pyongsan would yield a pretty low ore grade in the range of 0.01 to 0.03 weight% uranium. Now, this value is significantly lower than what had been reported previously, in which Pyongsan's ore grade was estimated to be 0.086% to 1 weight%, if not more. But there are few that are in agreement with the values that we are proposing in this study. For example, the Russian geologist Sazonov collected 7 sets of samples from carbon shells in North Korea and reported an ore grade that ranges from 0.002 to 0.03% uranium, much more in line with the values proposed in our study. Now, I also looked at uranium from Cambrian black shale deposits across the world that has similar geological settings and host rock ages. That includes the New Tintang uranium black shale deposit in southern China, as well as the alum shale in the Swedish Petura zone. And again, we see ore quality at these sites that agree well with the values proposed from our geological analysis. Estimating ore grade is really critical for understanding North Korea's nuclear capabilities. So to even better constrain this ore grade, I visited Okja Metamorphic Belt in 2019 to collect some of the rocks myself. So here's a video of a professor who guided me into the field, hammering the formation. The Pyongsan uranium mine was long reported as an anthracite coal mine by many. But if you look at these pictures that I took, these are featuring dark-colored, very fine-grained particles with some metalliferous layers and a lot of laminations. As you can see in this video here, these are highly deformed rocks that have undergone multiple stages of metamorphism under high heat and high temperature. And that's more like a shale rather than a coal. So what does it mean to have low ore grade? The constraining ore grade can tell us how much ore had to be processed in order to generate a certain amount of weapons materials. For example, in a scenario that North Korea has 900 kilograms of highly enriched uranium and 48 kilograms of plutonium, having an ore grade of 1% means that 66,000 tons of uranium-bearing ore had to be processed. Now that number increases to 330,000 tons when the ore grade decreases to 0.2% and almost 2.2 million when the ore grade decreases down to 0.03%, clearly highlighting the importance of better constraining this ore grade if we are to reduce the uncertainties in estimating the nuclear material stockpiles in North Korea. Now, interestingly, this low ore grade also means that it might be more challenging for North Korea to use this ore to generate nuclear energy, simply because you would need to process a lot of this low-grade uranium ore to provide sustainable fuel supply for electricity generation over long periods of time. But this low ore grade shouldn't be a huge bottleneck for making nuclear weapons, since you only need a few kilograms of enriched uranium in order to make a nuclear warhead. However, if North Korea wants to make a lot of weapons really, really fast, this low ore grade should be some constraints. Really briefly, there are other suspected uranium mines apart from Pyongsan, and I did conduct geological survey to look at 9 of the suspected and purported uranium mines of North Korea. But with the available information today, uncertainties remain as to whether or not these are indeed uranium mines. So that solves one variable of the equation, the ore quality. But how about the ore volume? How much of this low-grade ore does North Korea actually have? Now, typically, geologists will answer that by looking at a cross-sectional stratigraphy. And to simply put, this is just a slice of an earth to look at the profiles of the rock, just like how you would cut a slice of a cake to look at the cake layers rather than just the frosting at the top. An example of such is shown here for the Pyongyang Coal Formation in Tungsten Nap. There, uranium ore volume should be computed in rock layers, in the dimensions revealed in outcrops, in trenches, and in a lot of sampling from the drill holes. But none of that information is available to me at the scale that I need over the Pyongsan uranium mine. So then I ask an alternative question. How much uranium can North Korean mill actually process, and how fast can it do so? In other words, I'm asking, what is the yellow cake production capacity? Now, qualitatively, you can answer that by observing the mine waste expansion over time. Mine waste is just overburden and waste rocks that are generated during extraction of the ore. It's highlighted in this white stroke here. And as you can see, the mine waste at Pyongsan uranium mine has expanded in the last 14 years, indicating a continued production at the site. But this assessment is quite qualitative in that the ratio of mine waste to useful ore depends on many variables and it changes over time, making such estimates pretty crude. Now we can also detect the land use change. So using a platform provided to us by our company, Orbital Insights, we can see that the vegetation over Pyongsan uranium mine, represented by these 2 shades of green, have been reducing in the past 4 years, which is a possible sign that the mine is expanding. But again, the drawback of such method is that we are correlating vegetation change to mine expansion, which might not be very accurate. So in sum, quantifying ore volume by just looking at the mine is pretty inconclusive, and we need to turn to more complementary information. Some of this information can come from milling facility. Pyongsan milling facility is conveniently located less than half a kilometer away from the Pyongsan uranium mine. It has undergone pretty regular renovations and improvements to accommodate for the expanding capacity over time. There are a couple of factors here that can help us determine the yellow cake production capacity. That includes the size of the overall facility, size of the mill equipment, size of the mill tailing pile that increases over time, or the frequency of incoming and outgoing rail cars. Now, each of these individual factors alone might not tell us a lot of stories, but altogether, complementarily, these factors will guide us one step closer to our answer. But let's unpack the pathway from the mine to the mill before we get there. The satellite images indicates that ore at Pyongsan mine is being crushed in situ, as evidenced by these primary and secondary ore crushers. The crushed ore is then transported in the form of slurry through a slurry pipeline that is 500 meters long. Now, in a typical conventional uranium mill, the slurry is processed in the following steps. It undergoes further grinding if necessary, and then the uranium is dissolved out of the rocks through either acidic agent or alkalinic agent in the process called leaching. Leach solution then undergoes a solid-liquid separation process in which solid is being removed from the uranium-bearing solution. Uranium-bearing solution then undergoes chemical and physical processes to be purified and concentrated, after which they are dried out to remove the volatiles and impurities, and the final product is yellow cake. Yellow cake is then packaged into 55-gallon steel drums to be dispatched. Now, I tried to overlay these processes onto Pyongsan uranium milling facility, and here I propose just one possible processing pathway, although it is not necessarily the only way. But this scenario begins with this white building at the mine portal to which the slurry pipeline is connected to. The discoloration of the roof indicates dust accumulation, and that's pretty typical of a crushing and grinding facility at the mill. So it seems like additional crushing and grinding at Pyongsan mill is necessary to increase the surface area for leaching efficiency. Now, to pay attention to is the cellular tank that is connected to the grinding facility. A cellular tank is simply a large tank that can be used to recycle water for the grinding purpose. The size and the type of the cellular tank really varies, but at nominally 70-meter diameter, a cellular tank can hold a capacity between 380 to 1,500 tons of ore per day. And given the size of this overall milling facility, this cellular tank is most likely hold a maximum capacity of 1,000 tons of ore per day. The grinded particles then become leached. The leaching acid tank houses to the west of the grinding facility, and that's identifiable by the look of the rust on the roof. The rusting probably comes from the acidic gases that are being released during the leaching process. The leach products then undergo solid-liquid separation process, most typically associated with thickener units or countercurrent decontamination units, CCD units. The CCD units are just giant cylindrical tanks with a revolving rakes underneath and a walkway at the top. And depending on the mill, you could have either 2 of these tanks or 12 of these tanks or 16 of these tanks. Now, highlighted in this box is what could probably be the CCD units at Pyongsan to separate solid from its uranium-bearing liquid. These appear slightly smaller than the conventional thickeners used elsewhere, although CCD units of such size is not entirely uncommon. And if these are the CCD units, then the volume of these tanks corroborate to 1,000 tons of ore per day, in agreement with the cellular tank that we determined next to the grinding facility above. Based on the pipeline construction and the infrastructure of this building, we believe that this is for purifying and concentrating uranium, after which uranium is dried out in this 50-meter long rotary kiln, and that's just a giant furnace. The dried out solid yellow cake is then to be packaged to be shipped out. Most possibly happens in the southwest corner of the facility based on the proximity to the rail cars as well as the frequent observations of loading and unloading. Now, just to sum up our analysis from this mill equipment, a maximum capacity of 1,000 tons of ore per day means that if Pyongsan was operating 300 days a year, that's enough to produce materials to process 34 kilograms of plutonium. Now, this is under the assumption that the ore grade is 0.008% as we derive from the geological studies, and that the recovery rate at this milling complex is 80%. And that's enough to make somewhere between 4 to 6 nuclear warheads. Besides the mill equipment, another hint can come from looking at the mill tailings. Mill tailings are just waste and byproducts from processing of the uranium ore at the milling facility. At Pyongsan, the waste are being treated from this wastewater treatment plant, and the waste is then transported through a single pipeline to the natural lake basin behind a 4-meter high dam. Under the assumption that this is the mill tailings coming from processing uranium, increase in this volume can indicate how much yellow cake was produced at this milling complex. So here is a qualitative graph that shows tailings pile surface area increase from the year 2003. It's quite notable that in 2020 alone, the surface area has expanded quite a bit despite the summits between Trump and Kim. But the surface area is only going to give us limited information. What we really want to know is the 3-dimensional volume of this tailings pile. The change in volume over time can be computed with the specific gravity of waste solution as well as the ultimate density of settled tailings to get us one step closer to the answer. Such estimation is underway. Last but not least, complementary information can come from the rail car analysis. Now, there are 3 primary types of rail cars that we observe at this milling complex. That includes the open-top gondola type rail cars, most likely bringing in coal for the steam plants and minerals for reprocessing. And then we see a tank type rail cars, which are most likely bringing in chemical additives and reagents that need to be stored in the tank during the shipment. And then we see these flat top box cars. And in the Western world, it is these flat-top boxcars that carry yellow cake drums. So if North Korea is any same, then careful monitoring of these flat-top boxcars can tell us another hint as to how much yellow cake is being shipped out. We have one of the better temporal resolutions for observing activities at Pyongsan thanks to our partnership with Black Sky. We observe the activities at least once a week, if not once every 2 weeks, and we can confidently say that the activities at Pyongsan are ongoing as evidenced by the railcar movements, constructions, vehicles, etc. Now, everything processed from Pyongsan is to be transported to Yongbyon. We believe that this is done through rail cars. Yellow cake goes through 33 rail cars, 3 tunnels, and 2 bridges to arrive at the Yongbyon Municipal Dongan Rail Station. So from here on, I'll pass it on to Alison to tell you all about Yongbyon.
Hi, Solgi, thank you so much. And before I start, and before you mute your audio, I do want to say a little bit more about your railcar analysis. If there's time and interest, at the end of our presentation, Solgi's done a really interesting machine learning analysis of rail activity that's helped us sort of uncover yet another layer to our understanding of this part of North Korea's nuclear pathway. So perhaps after we can move forward with that. But at this point, let's talk about Yangchaon. So like Solgi's analysis of Pyongsan uranium mine and mill, we have been incorporating nuclear expertise-driven analysis of satellite imagery to our understanding of Yongbyon Nuclear Research Center. And by painstaking imagery analysis conducted at CSAC and a lot of esteemed organizations within the open source community, we can develop an evidence-based layer of empirical data to continually add to our understanding of the site. But unlike Pyongsan, we actually have a comparatively vast amount of specific contextual information to help us understand the status and ongoing activity at Yongbyon Nuclear Research Center. So for instance, Hans Blix and his IAEA inspection team took this video of the entire complex in 1992, which shows some of the numerous features within the complex. And our own CSAC cadre, including Professor Hecker, visited 4 times between 2004 and 2010, bringing back an unprecedented level of knowledge and understanding of North Korea's nuclear capability. Information about Yongbyon may certainly be scant compared to other nuclear facilities that comply to the status reporting standards of the International Atomic Energy Agency. But at CSAC, we've built a deep database of analysis derived from hundreds, now maybe thousands of satellite images taken over Yongbyon in the past decade and scrutinized by our in-house and out-of-house affiliated nuclear experts. Any trouble? Oh, there we go. So as Solgi mentioned, after the yellow cake is delivered by rail from Pyongsan uranium mill, it is brought into the only facility that by our best estimation can process or convert yellow cake into the materials you need to make weapons grade plutonium or the precursors to weapons grade highly enriched uranium. This is Yongbyon Nuclear Research Center. So yellow cake can be transported into a factory and used to make uranium metal fuel rods that can be inserted into North Korea's 5 megawatt gas graphite reactor. The spent fuel from these rods can be processed into weapons grade plutonium. And also, yellow cake is brought into the fuel enrichment and fabrication complex at Yongbyon and can be converted into a compound called uranium hexafluoride, which once cascaded through a series of centrifuges becomes enriched uranium. Enrich it long enough and it becomes weaponizable, and you can use this or the plutonium to make a bomb. For a quick orientation, Yongbyon Nuclear Research Center is about 100 miles north of Pyongsan through the capital of Pyongyang. It is home to North Korea's only continuously operational nuclear reactor, the 5 megawatt gas graphite reactor, which has been used to create North Korea's stockpile of weapons grade plutonium. Here in the center of Yongbyon is where the spent fuel rods are processed for plutonium extraction. The centrifuge halls are in the southern portion of the facility, and just south of the 5 megawatt reactor is North Korea's as yet inactive experimental light water reactor. So let's take a closer look at the uranium pathway from yellow cake to weaponizable enriched uranium. We believe yellow cake comes by rail from Pyongsan uranium mill to this railroad terminus. Nearby, other chemicals necessary to create the enrichable uranium compound are manufactured and are then brought to this pretty large uranium conversion facility. This is about the length of a football field. The yellow cake is also brought into the same building, and it's reacted with the other agents to produce uranium hexafluoride, which is the enrichable compound. The resulting compound is then brought into the centrifuge halls and processed until it becomes low enriched uranium. Now, we believe they then ship the LEU in canisters to another enrichment facility, possibly a site known as Kangsan, or even another unknown place for further enrichment into weapons grade highly enriched uranium. That's the process for enriched uranium. Here's the process from yellow cake to plutonium. There is another dedicated rail line into the facility of Yongbyon here next to the 5 megawatt reactor. We're theorizing this is where they manufacture the uranium metal fuel rods, which are inserted into the 5 megawatt gas graphite reactor. They reside there for an extended period of time, during which the fissioning of the uranium-235 in the fuel rods in the reactor causes a neutron reaction to produce a plutonium isotope suitable for weaponization. Open sources theorize the 5 megawatt reactor can process enough fuel rods to produce about 6 kilograms of plutonium roughly in a year. And after the fuel rods are processed, they are removed from the reactor and placed in a cooling pond until cool enough to be moved to the plutonium reprocessing facility for plutonium extraction from the spent fuel rods. Those fuel rods are transported to the center of Yongbyon and enter a massive building in which weapons-grade plutonium is chemically extracted from the rods. The resulting weapons-grade plutonium, of which there's just a small amount, we're talking kilograms of it, is shipped from Yongbyon to the next step of the plutonium pathway in which a weapon is fabricated from this material. Next slide. So after a long time of expert-driven analysis of satellite imagery, we feel we have a comfortable read on the status of Yongbyon. First, the 5 megawatt reactor has been inactive since at least December 2018. We can see there is activity around the reactor, but our visual signatures of patterns that signify reactor criticality have been more or less absent since 2018. What we have been seeing, though, is that the reactor operators keep engaging and disengaging the cooling systems of both reactors, as you can see in this form of water effluent emanating from the cooling outfall lines into the Korean River nearby. This has happened repeatedly over 2020 and has not only managed to drive me crazy as an imagery analyst, but it tells us something interesting. So you can't just turn on and off a reactor or that reactor's cooling system. So why are we seeing engagement and disengagement of a system that needs to be continuously active? We believe it's because the North Koreans have been implementing, upgrading, or repairing both reactor cooling systems, and the engagement and disengagement has been a part of this process. And furthermore, unprecedented flooding during the summer of 2020 may likely have damaged or hindered progress construction at these critical cooling systems. And finally, as a reminder, although the construction of the light water reactor began a decade ago, it is not yet critical today and never has been. Accordingly, the plant that is used to extract plutonium from the reactor's spent fuel rods has activity, but not the kind that verifies plutonium reprocessing is underway. So the reactors have not been engaged, the plutonium reprocessing has not been engaged, but the yellow cake intake, the yellow cake uranium conversion, and the centrifuge uranium enrichment halls have been consistently active over the past few years. So from this analysis of reactor criticality and centrifuge activity at Yongbyon, we can glean perhaps not an exact figure, but a fairly decent ballpark range of how much weapons-grade material North Korea is capable of making and how much weapons-grade material they already have.
Thanks, Alison. So I know that that was a pretty dense presentation, so I'll just end here. But we hope that we demonstrated the multidisciplinary approach to understand the uranium pathway in places like North Korea with the lack of on-site access. From geological analysis, we could tell that the Pyongsan ore grade is lower than what had been reported previously, and the ongoing analysis of satellite images indicate that both Pyongsan and Yongbyon are active, although the criticality level at Yongbyon has not been detected since 2018. There's 3 different technical and policy implications from our study. We're introducing a new toolset or new method for better understanding and verifying North Korea's nuclear capabilities. We're contributing to the open source research and adding information to the intelligence community as well as the government agencies, thereby allowing policymakers to have more informed decision-making process. And here I'm just going to advertise our talk for next week, led by Alison Puccione, titled Remote Sensing for Environmental and Economic Security in North Korea. So that's going to be North Korea Part 2. With that, we would love your feedback and look forward to the discussions.
Thank you, Solgi. Thank you, Alison. Sorry, just trying to let the fire truck go by. Well, I guess we'll proceed. Just as a reminder to everybody, if you have a question for Solgi or Alison, please go ahead and enter in the Q&A function of Zoom. Let me start out with a couple of questions that I think might be related. The first question is focused on the sources of North Korea's technology for engaging in the activities you've been discussing in this presentation. To what extent is it homegrown? To what extent are they acquiring it abroad? And to what extent are they then turning around and exporting it or selling it?
Am I muted? No, I'm not muted. Thank you for the question. So we actually don't know if North Korea has been importing this technology or if they are reselling it. I don't doubt that North Korea has been engaging in some form of import or export of either fissile materials or other nuclear-related technologies. But at least when it comes to export and import of fissile materials, the veracity of such import and export is not really easy to confirm. So I cannot answer with the information that I have today as to how much it has been imported or exported. But I guess when it comes to the fissile materials, the criticality of our study is that it provides a platform for understanding the whole picture. So in the future, if you can confirm that, oh, North Korea's ore grade was this or the ore volume was that, and the uranium production capacity at the milling facility is this, then we can combine such information with other available sources from nuclear archaeology or nuclear forensics to compute how much is missing that could have been exported or how much is a surplus that could have been imported. As to the technology, I think North Korea might have learned some stuff from Soviet Union, but I don't know to what extent they had actually imported this technology.
Yeah, Harold and Solgi, I don't have too much to add. It's not quite my area of expertise. Obviously, as Solgi mentioned, I believe their mining capability predates even the Korean War. I know that the Soviets helped with the research reactor, and if I'm not mistaken, part of the 5 megawatt in the 1980s. The research reactor was several decades before that. However, and I believe it was Jeffrey Lewis said, you know, they did have a little bit of help getting the nuclear program started, but their reactor program and even their missile program kind of looked something like China's in domestic capability and evolution of their own reactor and missile program. And as far as the cross exchange of technical information, we do believe, I believe in the research that I've done over the past 10 years, that we have seen North Korea working with Iran in their at least missile or nuclear technology. And if I'm not mistaken, about 10 years ago, I came across some information that led me to believe that North Korea was exporting some kind of information about the machining of ingots that may have to do with nuclear materials to Burma. So I do know that there may be a little bit of exchange, but I know that exports quite heavily sanctioned, quite heavily watched. I know it takes place, but I'm afraid I can't get too much more into it. I simply don't know.
Thank you. And Solgi, maybe follow up from Rod Ewing on the milling facilities, such as clarifiers. Mm-hmm. Do you have any more specific information on whether that's sort of developed in the DPRK or is that imported?
Oh, I don't know if it was imported. I think it's a pretty standardized milling techniques that didn't have to be imported, but I'm not sure. Yeah, I can check that, but I don't think it was. Yeah, I'm not sure what the answer.
Great. Let me go to Pavel Podvig and then to Scott Sagan and followed by Gabriel Hecht. So Pavel asks, how confident are you that there's no conversion facility outside of Yongbyon?
That's a great question. So it is absolutely impossible for me as an imagery analyst to prove a negative. I do know that the conversion facility that we do see within the fuel enrichment and fuel fabrication plant at Yongbyon has been pretty consistently active. We can tell by a pretty visible stream of effluent, smoke effluent coming from out of the roof. I have been asked this question, Pavel, quite a bit, to the extent that I suspect there may be another enrichment facility. I just simply haven't seen it. Much like Kangsong, the another enrichment facility, it's difficult to look at a large building without much context and say this building is X meters long by X meters wide and it has a smokestack, therefore it could be a uranium enrichment facility or a centrifuge enrichment facility for that matter. This is kind of a long-winded way of saying I'm not really sure.
Okay, going on to Scott Sagan's question. Scott Sagan here at CSAC. What does your analysis tell us about the risk of North Korea selling its yellow cake to other states, such as Iran and Syria?
I'm not sure if analysis really points to the fact that it is selling yellow cake to other countries. From my analysis, the grade of uranium is pretty low, and I don't think North Korea has as much as yellow cake as what other reports have previously have said. Having said that, I would think that if North Korea is wanting to make more nuclear weapons, it would keep it for themselves rather than for exporting to Iran or other countries. But it's hard to track whether or not they are actually selling this to other countries. Alison, do you have anything else to add?
Yeah, I'll only kind of parrot what you said earlier. If the ore grade is anything near what Solgi's been saying, it doesn't seem like a great economy of trade for them to sell yellow cake, and especially with the sanctions. However, I know that there have been instances where North Korea has tried to ship sanctioned items like a surface-to-air missile system, et cetera, but there is so little, it seems like there may be so little in yellow cake that it might not be sold.
Great. From Gabriel Hecht at CSAC. Thank you both for presenting this fascinating work. It reminds me of the work done by anti-apartheid activists in the 1980s who were seeking to document South Africa's nuclear weapons program by analyzing the operation of a uranium mine in Namibia. Your approach is much more sophisticated and technical, of course. How do you see your results affecting politics or policy?
I guess I can tie that into some of the conclusions that I presented, but it's a new tool set, but not really new from the geological perspective, but it seems like in the intelligence community, the geological analysis has not really been implemented. So in that sense, I feel like we're introducing a new method for just another way of verifying North Korea's nuclear weapons capabilities that have not been used previously. And perhaps that can inform policymakers for a better decision-making process in the future during the negotiation processes.
Great. Let me go to a couple of the questions in chat. From Betty Suh. She says, thanks so much for this talk, very insightful. Wondering whether you're applying any AI machine learning or other algorithms when analyzing all this imagery. There must be a huge amount of satellite imagery that you're now analyzing and comparing.
So Harold, could you repeat the question? I think I lost you for a minute there.
Okay, it's Betty says, I'm wondering whether you're applying any AI machine learning or other algorithms when analyzing all this imagery. It must be a huge amount of satellite imagery that you're analyzing and comparing.
Yeah, it is a lot of satellite images. Maybe next week, if we're running out of time, we can show you what we are doing in the collaborative company Orbital Insights, but they have a platform where we can combine commercial images with artificial intelligence and data science models. So we can go through hundreds and hundreds of images within less than a day to track for a couple of the factors that can hint us that the proliferation activities are ongoing. If you have time at the end, if the audience is still interested, we can quickly showcase that, but let's try to answer those questions. first.
Yeah, I will add that Sulgi's been actually working specifically on sort of machine learning extracted evidence from satellite imagery. Her rail study that she talked about a little bit earlier in the presentation was kind of alluded to that.
So one more question from chat from Vitaly Fichenko. Thank you for your presentation. Have you considered a possibility of North Korea obtaining uranium from phosphate ores? If so, what is your assessment of it?
Yeah, phosphate ore and uranium has garnered some attention in the last few years. North Korea does have some phosphate limestone in the area surrounding the Pyongsan uranium mine. The Pyongsan mine is sitting in a sedimentary basin called the Pyongnam Basin. And surrounding the Pyongsan Basin, we do see some, from the geological map analysis, we do see some phosphates. However, I can only speak to the Pyongsan milling facility, and I do not see any direct evidence that they are processing uranium from phosphate fertilizers at the Pyongsan milling facility. I'm not an expert at phosphate limestones or anything, but they would require different types of mill equipment. That you would need more cellular tanks, and you would need a different types of sedimentation ponds to process that. And at least from the satellite images of Pyongsan, we do not see those. So from my analysis, I don't think Pyongsan milling facility is used to extract uranium directly out of the phosphate fertilizers. Having said that, there is a possibility that the pre-treatment from phosphate fertilizers occurs somewhere else, and they are bringing in the pre-treated materials to be processed at milling facility at Pyongsan. But so far, I do not see any direct evidence of that happening.
Great. From Jamie Whitthorne, says, hi, Alison and Sulgi, great presentation. I have a few questions. Could you speak more about how you implemented machine learning into analysis of the rail cars? I'm specifically curious about your data set development and any respective limitations it might have had. And for Alison, could you please elaborate a bit more on your uranium conversion analysis? It was my understanding it's currently unknown where the UF4, UF6 production is occurring officially. So I was interested in how your analysis suggested that fluorination, hydrofluorination was occurring at the old UO2 production building at the fuel fabrication plant.
Alison, do you want to answer your question first, but I pull up some screen?
Yeah, hi, Jamie. It's a really good question. I've had that question a number of times. I would be very happy to talk to you offline about that. It's been my understanding that the activity that we've seen at the fuel enrichment and fuel fabrication plant has indeed been the yellow cake reacting with hydrogen fluoride to make UF6. But you're right, I've had that question quite a few times. It's very possible that it may be happening somewhere else, but we have seen activity at what we're calling the sort of uranium conversion plant pretty continuously for the last 5 or 6 years.
Can everyone see the screen I just shared?
Mm-hmm.
Jamie, it's good to see you here. So we have an emergence of data set made available from like hundreds of commercial satellite images being launched into space. And it really made the analysis of observing and monitoring Yongbyon or North Korea much easy. But we have like huge data sets that we need more than just manpower. So we actually collaborate with a company called Orbital Insights. And to me, it's a leading company in a global effort that unites commercial satellite images with computer vision algorithms, data science models. Using the platform that they provided, so this is the platform from Orbital Insights, we ran an object detection algorithm model to basically detect rail cars at Yongbyon as well as in other places in North Korea. I wanted to show you the actual platform, but I noticed that if I click on it, I'm going to lose the screen. So I'll just try to explain to you. But the platform has over 550 images about Yongbyon, and it detects rail cars. I don't know if you guys can see this, but these are tiny little rail cars, and they toggle it with the brown spots. And they do this over 550 images to tell us, oh, here there are sturdy rail cars, or here this image they have no rail car, and here this image is over 50 rail cars, and they basically get us the answers in 24 to 48 hours. So this is one of the ways that we applied artificial intelligence into the commercial satellite images to track for the proliferation activities, how often or how frequent the rail cars are appearing and disappearing at Yongbyon. Alison, do you have anything else to add?
Just that automated analysis has been a godsend to us. We actually used to try to count vehicles by hand over hundreds of images, you know, human beings, but this has really been helpful to help us large amounts of data.
Sorry, there's clearly something going on in Redwood City. Okay, I guess the fire truck has gone by now. Let me jump ahead to some questions from our CSAC pre and postdoctoral fellows. We usually lead off with their questions, but they didn't have any at the beginning of the Q&A session. Let me bring them in now. From Ryan Musto, what an impressive research, what a visually stunning presentation. No doubt North Korea's leadership is aware that satellite imagery offers the potential for such insights into their progress. Over the course of your research, have you seen attempts by North Korea to further disguise its nuclear fuel cycle capabilities, or has the program pretty much proceeded along the same path? Could dissemination of your research actually result in further evasion tactics?
Okay, I'll start if that's all right. Yeah, absolutely. It's an excellent question. It's a question we get commonly. I do believe that it is, North Korea has been aware of the commercial satellite imagery orbital patterns. I believe that North Korea launched a Yongbyon-2 rocket in 2009, and my hunch is that they actually waited for the commercial satellite Worldview 2 to come into overpass while they launched. So not only do they use satellites to maybe project their strategic prowess, but you're absolutely right. We do believe that they have worked on concealment efforts, specifically at Yongbyon Nuclear Research Center, to obfuscate some of the telltale patterns that we use to verify whether a reactor is active or not. I think it was Melissa Hannum who said it's something like a long game cat and mouse section where they obfuscate and we study it until we figure out a way to understand it. We understand it, we publish, they go and obfuscate, and then we continue to do that. It's the way of the tradecraft. It's going to happen no matter what. You know, the process is we just keep continuing to look and continuing to identify different patterns that help us understand what's going on. Thanks for your question.
No, I echo what Alison said. When it comes to the milling facility, I don't see as many covert activities as it probably has happened in Yongbyon or other places. But I definitely have that in mind. What if they're covering the CCD tanks in a building that we can't see and we can't identify? But at least so far, I've been checking the constructions since 2003 at least, and it doesn't seem to have so much covert activities, at least on the milling side.
Thanks. Let me go to a question now from Jeff Ding. He asks, fascinating research. He says, I know it's hard to say, but to what extent do you think that National Intelligence Agency assessments of North Korean capabilities apply similar methods as your research? And sort of curious about the interaction between OSINT communities and intelligence communities on this.
I'm sure they use satellite images more often than we do. I don't know if they're using geological analysis. I highly doubt that. I don't see many of the people using geology as a tool set to understand such stuff in the intelligence community.
And Harold, I officially am not touching that with a 50-foot pole. I will not say whether I would even know what the intelligence community is capable of. I just know that the commercial satellite imagery is giving us enough information to make really well-estimated guesses, and also usher in a layer of transparency into the media that helps us to better understand the world around us.
Thanks. Let me go now to Sig Hecker at CSAC. Great job, Solgi and Alison. Solgi, Kim Jong-un just made nuclear power an important goal in his 8th Workers' Party Congress, but for that he needs a sufficient domestic source of uranium. Do you yet have a sense that they may have enough uranium for a serious nuclear electricity program?
Thank you, Sig, for the question. I think I said it in the middle of the talk, and I'll reiterate here. The ore grade that we derive from the geological analysis says that you probably need a whole lot of processing in order to make enough low enriched uranium to generate electricity for a long period of time. to me, it doesn't seem like it would be easy for North Korea to use this ore to generate nuclear energy. I don't think they have as much ore as what people would usually assume. So they would definitely have enough to make nuclear weapons if they wanted to. I hope that answers the question.
Great. Let's go now to Jason Bartlett from CNAS in Washington, D.C. Thank you, Seulgi and Alison, for a great presentation and sharing your research. Have you seen any significant developments in recent years in North Korea's indigenization methods and capabilities for mining and extracting ore? The frequency, success, amount, etc. Policymakers and sanctions frameworks often focus mainly on deterring foreign assistance, but not on indigenized skills.
Thank you, Jason. I don't know if they made any significant developments in the indigenization methods. However, I should say that we still see the expansion of the mill tailings pile over time, especially in 2020, as I've showed in the small figure in one of the slides. So they're definitely continuously producing it. And I know that they are constantly renovating to increase the capacity of the mill. I know they have a lot of constructions and they're building extra buildings and stuff, but I don't know to what extent they're actually improving their methods.
Great. I think we probably only have time for maybe one or two more questions. We go to Cameron Tracy, former CSAC fellow. He asks, could aerosol sampling provide a useful complementary input to your assessment of production activities? Scott Kemp's work on the transport of oxyfluoride from enrichment activities suggests that detection over several hundred kilometers might be feasible.
Go ahead, Seulgi.
Oh, I never heard about this, but I think we should definitely look into it. Thank you, Cameron, for providing us that information.
Yeah, Cameron, I'd love to speak with you offline. You know what, I'm not going to speak to this. I'm wondering what you mean specifically by aerosol activity. Certainly if it's visible remotely, you know, or even from like a multispectral or thermal perspective, that might be interesting, but I would love to speak to you offline.
Great. And let's take a question from David Hall. Thank you both for the talk. I found it extremely informative and insightful. At the beginning of the talk, you mentioned about flooding in 2020. And as we know, flooding in the 1990s damaged a lot of North Korea's infrastructure. Can you speak a little bit more about how volatile and susceptible to damage these mines and processing facilities are?
I would love to speak about the cooling systems. Perhaps Seulgi obviously would have much more expertise on the mines and mills, but yes, exactly right. The Korean River is the lifeblood for the cooling facilities, both the 5-megawatt reactor, which used to have a cooling tower until 2008, where they ceremoniously blew it up after some diplomatic detente. But now they rely on filtered cold water from the Korean River to cool it. And every time there's a flood, it overflows this choke point that they have in the river so that it dams up enough water to flow into the intake and the cisterns for the 5-megawatt and presumably the ELWR as well. So we know from Nick Hansen's excellent work in 2012 that flooding, I believe, yeah, in 2012 stopped the operational capability of the 5-megawatt reactor after overflowing the cooling system. The flooding that I saw in August of this year was worse, a lot worse than 2012. And I believe some of the engagement and disengagement of the cooling system was a result from that flooding. So long story a bit shorter, if you they just simply do not have enough control over the Korean River to sustain continual perfect operation of the cooling, the cooling through line.
When it comes to the mines and the milling facilities, they may be wrong, but I don't think the mining and milling facilities is as volatile and susceptible to flooding damage as it is the cooling systems at Yongbyon. I didn't see any halting of activities because of the flood in 2020. The activities were constantly ongoing.
I'll add, and this is a bit off topic, I apologize, but the Punggye Nuclear Test Site had a number of tunnels, one of which I think it was the south tunnel flooded in 2012, and they spent months pumping water out of that. So it's quite susceptible to flooding, and the nuclear reactors themselves are very susceptible.
Great. Well, we're at time, so I think we'll leave it there. We'll obviously pass along the remaining questions to Silgi and Alison. They can follow up separately. Please join me, everybody, in thanking Dr. Park and Alison Puccione for an excellent presentation.